NEC 220.30C6 allows for a reduced load calculation for service conductors, which includes generator sizing, considering 80% for continuous loads and 100% for non-continuous loads. NEC 424.3b requires branch circuits supplying continuous loads, like heating, to be rated at 125% of the continuous load. It is critical to recognize that service conductors, including those used for generator sizing, are distinct from branch circuits. Therefore, NEC 424.3b does not directly dictate generator load calculations. Instead, NEC 220.30C6 is the governing article, specifically designed to allow a reduced load calculation for service conductors, including generators, which accounts for the continuous nature of certain loads and the statistical improbability of all loads operating at their maximum demand simultaneously. It is essential to understand that NFPA opinions are not legal mandates and cannot be enforced by inspectors as if they were code. The NFPA opinion cited, which suggests heating should always be figured at 125%, lacks specificity regarding generator load calculations. It does not supersede the explicit provisions outlined in NEC 220.30C6. When engaging in a discussion with an inspector, it is beneficial to firstly present the relevant NEC articles, particularly NEC 220.30C6, and how it directly applies to the situation. Secondly, clearly explain the difference between branch circuits and service conductors, emphasizing that NEC 220.30C6 is intended for generator sizing and service conductor calculations. Thirdly, highlight the purpose of NEC 220.30C6, which aims to ensure that generators are appropriately sized to handle real-world loads while also considering the actual operating characteristics of those loads, reducing the likelihood of oversizing and unnecessary costs. Fourthly, if available, provide supporting documentation from reputable sources, such as generator manufacturers or industry experts, which supports the interpretation of the NEC code being presented. Finally, remain open to compromise. While it is important to defend one's position based on code and best practices, it might be necessary to reach a compromise by including the heat load in the calculation if the inspector remains unconvinced. However, it is crucial to document any objections and the reasons for any compromise made to protect oneself and to ensure transparency. The ultimate decision regarding whether to include the heat load at 125% rests with the inspector. However, by presenting a well-reasoned and thoroughly documented argument based on the relevant NEC articles and industry standards, one can attempt to persuade the inspector to accept the more accurate and appropriate load calculations. Understanding electrical load calculations, particularly for generators, requires careful consideration of the National Electrical Code, or NEC. The NEC provides guidelines to ensure safety and proper sizing of electrical systems. For generators, this involves calculating the total load that the generator needs to support. Key to this is understanding continuous and non-continuous loads. Continuous loads are those expected to operate for 3 hours or more at a time. Non-continuous loads are those that operate for less than 3 hours. The NEC specifies different methods for calculating these loads. When sizing a generator, it is important to consider both the continuous and non-continuous loads. Continuous loads are typically multiplied by 125% as a safety factor to account for the extended operation and potential for overheating. Non-continuous loads are added at 100% of their value. It is also important to consider any motor loads, as motors can have high inrush currents when starting. These inrush currents can significantly increase the instantaneous load on the generator. The NEC provides guidelines for calculating motor loads, often requiring them to be calculated at a higher percentage of the nameplate rating. Another factor to consider is the power factor of the loads. Power factor is a measure of how effectively electrical power is being used. A low power factor can increase the current drawn by the loads, which can affect the generator's capacity. In some cases, power factor correction may be necessary to improve the efficiency of the system. The NEC also provides guidelines for derriting generators based on altitude and temperature. Generators operating at high altitudes or in high temperature environments may need to be derated to account for the reduced air density and cooling capacity. This derating ensures that the generator can operate safely and reliably under those conditions. In addition to the NEC, local codes and regulations may also apply. It is important to check with the local electrical inspector to ensure that the generator installation complies with all applicable requirements. This can help to avoid any issues during the inspection process and ensure the safety of the electrical system. Calculating generator loads involves several steps. Firstly, identify all the loads that the generator will need to support. Secondly, determine whether each load is continuous or non-continuous. Thirdly, calculate the load for each continuous load by multiplying its value by 125%. Fourthly, add up all the continuous and non-continuous loads, as well as any motor loads. Fifthly, consider the power factor of the loads and make any necessary corrections. Finally, derate the generator based on altitude and temperature if necessary. By following these steps and adhering to the NEC and local codes, one can accurately calculate the load requirements for a generator and ensure that it is properly sized for the application. Understanding the different types of electrical loads is crucial for accurate load calculations. Electrical loads can be broadly categorized as resistive, inductive, or capacitive. Resistive loads, such as incandescent lights and electric heaters, have a power factor of 1, meaning that the voltage and current are in phase. Inductive loads, such as motors and transformers, have a lagging power factor, meaning that the current lags behind the voltage. Capacitive loads, such as capacitors and some types of electronic equipment, have a leading power factor, meaning that the current leads the voltage. The power factor of a load can significantly affect the amount of current it draws. A load with a low power factor will draw more current than a load with a high power factor for the same amount of power. This increased current can overload the generator and cause it to overheat. Power factor correction can be used to improve the power factor of a load. This involves adding capacitors to the circuit to offset the inductive reactance of the load. Power factor correction can reduce the current drawn by the load and improve the efficiency of the electrical system. The NEC provides guidelines for power factor correction, including the size of the capacitors needed and the location where they should be installed. Another important aspect of load calculations is demand factors. Demand factors are used to reduce the calculated load based on the assumption that not all loads will be operating at their maximum capacity at the same time. For example, a demand factor of 0.8 means that the calculated load can be reduced by 20%. The NEC provides demand factors for various types of loads, such as lighting, appliances, and HVAC equipment. These demand factors are based on statistical data and engineering judgment. It is important to use the appropriate demand factors for each type of load to avoid oversizing the generator. However, it is also important to be conservative and not underestimate the load requirement. In some cases, it may be necessary to use a higher demand factor or no demand factor at all to ensure that the generator can handle the actual load. In addition to demand factors, diversity factors can also be used to reduce the calculated load. Diversity factors are similar to demand factors, but they are applied to multiple loads of the same type. For example, a diversity factor of 0.75 applied to 10 lighting circuits means that the calculated load for those circuits can be reduced by 25%. Diversity factors are based on the assumption that not all loads of the same type will be operating at their maximum capacity at the same time. The NEC provides diversity factors for various types of loads, such as lighting, appliances, and HVAC equipment. It is important to use the appropriate diversity factors for each type of load to avoid oversizing the generator. However, it is also important to be conservative and not underestimate the load requirements. In some cases, it may be necessary to use a higher diversity factor or no diversity factor at all to ensure that the generator can handle the actual load. Proper grounding of the generator is also essential for safety. The grounding system provides a path for fault current to flow back to the generator, which can help to prevent electrical shock and equipment damage. The NEC provides detailed requirements for grounding generators, including the size of the grounding conductors and the location where they should be connected. The grounding system should be inspected regularly to ensure that it is in good condition and that all connections are tight. In addition to grounding, surge protection is also important to protect the generator and the connected equipment from voltage surges caused by lightning or other electrical disturbances. Surge protectors are designed to divert excess voltage away from the equipment into ground. The NEC provides guidelines for surge protection, including the type of surge protectors needed and the location where they should be installed. Surge protectors should be inspected regularly to ensure that they are functioning properly. Regular maintenance of the generator is also crucial for its reliable operation. This includes checking the oil level, coolant level, and battery voltage. The air filter should also be cleaned or replaced regularly. The generator should also be started and run periodically to ensure that it is in good working order. The maintenance schedule should be based on the manufacturer's recommendations and the operating conditions. Proper ventilation is also important for generator operation. Generators produce heat, and if they are not properly ventilated, they can overheat and fail. The NEC provides guidelines for generator ventilation, including the amount of air required and the location of the ventilation openings. The ventilation system should be designed to prevent the recirculation of exhaust fumes. The exhaust system should also be designed to prevent the entry of rain or snow. Fuel storage is another important consideration for generator installations. Fuel storage systems should be designed to prevent leaks and spills. The NEC provides guidelines for fuel storage, including the type of tanks allowed, the location where they should be installed, and the fire protection requirements. The fuel storage system should be inspected regularly to ensure that it is in good condition and that there are no leaks. Transfer switches are used to switch between the utility power and the generator power. Transfer switches can be manual or automatic. Manual transfer switches require the operator to manually switch between the two power sources. Automatic transfer switches automatically switch to the generator power when the utility power fails. The NEC provides guidelines for transfer switches, including the type of switches allowed, the location where they should be installed, and the wiring requirements. Transfer switches should be inspected regularly to ensure that they are functioning properly. When installing a generator, it is important to consider the noise level. Generators can be noisy, and if they are located near residential areas, they can cause a disturbance. The NEC does not specifically address generator noise levels, but local noise ordinances may apply. Noise reduction measures, such as sound enclosures or mufflers, may be necessary to comply with local regulations. Permits are typically required for generator installations. The permit process ensures that the installation complies with the NEC and local codes. The permit application will typically require detailed drawings of the installation, including the location of the generator, the wiring diagram, and the grounding system. The installation will be inspected by the local electrical inspector to ensure that it meets all applicable requirements. Coordination with the utility company is also important for generator installations. The utility company may have specific requirements for connecting the generator to the utility grid. These requirements may include the use of a specific type of transfer switch and the installation of protective devices to prevent the generator from backfeeding into the grid. Failure to comply with the utility company's requirements can result in the generator being disconnected from the grid. Understanding the NEC is a continuous process. The NEC is updated every 3 years, and it is important to stay current with the latest changes. The NEC changes can affect generator installations, and it is important to be aware of these changes to ensure compliance. Continuing education courses and industry publications can help to stay up to date with the NEC. Accurate load calculations are crucial for selecting the right size generator. An undersized generator will not be able to handle the load, which can result in power outages and equipment damage. An oversized generator will be more expensive to purchase and operate. Proper load calculations will ensure that the generator is sized correctly for the application. Safety is always the top priority when working with electrical systems. Generators produce electricity, and it is important to take precautions to avoid electrical shock. Always disconnect the power before working on any electrical equipment. Use insulated tools and wear appropriate personal protective equipment, such as gloves and safety glasses. If you are not comfortable working with electrical systems, hire a qualified electrician. The NEC is a complex document and it can be difficult to understand. If you have any questions about the NEC, consult with a qualified electrician or electrical engineer. They can provide guidance on how to comply with the NEC and ensure the safety of the electrical system. Continuous loads, as defined by the NEC, are those where the maximum current is expected to continue for 3 hours or more. This is a critical distinction because continuous loads require different treatment in load calculations compared to non-continuous loads. The NEC mandates that the portion of a branch circuit that supplies continuous loads be rated at 125% of the continuous loads. This is intended to prevent overheating of the wiring and devices. The 125% factor is applied to the continuous load before adding it to the non-continuous load to determine the total branch circuit load. For example, if a branch circuit supplies a continuous load of 10 amps and a non-continuous load of 5 amps, the total load calculation would be 10 amps 1.25 plus 5 amps equals 17.5 amps. This means the branch circuit needs to be rated for at least 17.5 amps. In contrast, non-continuous loads are those where the maximum current is not expected to continue for 3 hours or more. These loads are added at 100% of their value to the load calculation. The distinction between continuous and non-continuous loads is important for sizing branch circuits, feeders, and services. It is also important for sizing generators, as the NEC allows for a reduced load calculation for generators that supply both continuous and non-continuous loads. However, the 125% factor for continuous loads must still be applied to the branch circuits applying those loads. It is also important to note that some loads may be considered continuous even if they do not operate continuously for 3 hours or more. For example, a load that cycles on and off frequently may be considered continuous if the average current draw over a 3-hour period is high enough. The determination of whether a load is continuous or non-continuous should be based on the expected operating conditions and the manufacturer's specifications. NEC provides guidance on how to determine whether a load is continuous or non-continuous, but it is ultimately up to the electrical designer to make the determination based on their professional judgment. The load calculation should be documented to support the determination. Understanding the different types of overcurrent protection devices is also important for electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Circuit breakers are reusable devices that trip when an overcurrent occurs. Fuses are one-time devices that melt when an overcurrent occurs. The NEC provides requirements for the selection and installation of overcurrent protection devices. The overcurrent protection device must be sized to protect the conductors and equipment that it supplies. The overcurrent protection device must also be of the correct type or the application. For example, time delay fuses are often used for motor circuits because they can withstand the high inrush currents that occur when motors start. The overcurrent protection device must be installed in a readily accessible location. The overcurrent protection device must also be labeled to indicate its ampere rating. The overcurrent protection device should be inspected regularly to ensure that it is functioning properly. Ground fault circuit interrupters, or GFCIs, are another important safety device. GFCIs are designed to protect people from electrical shock. GFCIs detect ground faults, which are unintended electrical paths to ground. When a ground fault is detected, the GFCI trips, interrupting the flow of electricity and preventing electrical shock. The NEC requires GFCIs to be installed in certain locations, such as bathrooms, kitchens, and outdoor areas. GFCIs should be tested monthly to ensure that they are functioning properly. Arc fault circuit interrupters, or SIs, are designed to protect against electrical fires. SIs detect arc faults, which are dangerous electrical arcs that can occur in damaged or deteriorated wiring. When an arc fault is detected, the FSI trips, interrupting the flow of electricity and preventing electrical fires. The NEC requires FSIs to be installed in certain locations, such as bedrooms and living rooms. FSIs should be tested monthly to ensure that they are functioning properly. Electrical safety is a shared responsibility. Everyone should be aware of the hazards of electricity and take precautions to avoid electrical shock and electrical fires. By following the NEC and using appropriate safety practices, it is possible to create a safe electrical environment.